In this video, we're going to talk about redox titrations. We're on the last section of chapter 4. Okay, so we've already talked about gravimetric analysis and acid-base titrations, gravimetric analysis and titrations, so both acid-base and redox titrations. These topics are all offshoots of what we talked about in section 4.5 on concentration of solutions. We learned that in order to think about discussing quantities of reactants and products in a chemical reaction that occurs in solution, we need some new terminology. The quantity of a substance in solution is expressed by stating the concentration of that substance in the solution. So there's different ways of expressing concentration, but in this chapter, we're only talking about the most common unit of concentration, molarity. Molarity is also known as molar concentration, and it's the number of moles of a specific solute per liter of solution. So also in this chapter, we're only thinking about solutions in which the solvent is a liquid. So with molarity, then, we're thinking about how the molarity of a specific substance in a solution is a specific solute is the number of moles of that solute divided by the total volume of the solution, of the liquid solution. Okay, so that's how you express the quantity of a specific substance in solution, by stating the concentration of that substance in the solution. All right, now, analyzing quantities of reactants and products in a chemical reaction, we know is stoichiometry, right? That's stoichiometry. Stoichiometry is the study of the quantitative relationships between reactants and products in a chemical reaction. And so after learning the meaning of concentration in section 4.5, the rest of the chapter is about solution stoichiometry. And in these last 3 sections, we're focusing on 2 techniques that are used to study solution stoichiometry: gravimetric analysis and titrations. Okay, so as we talked about previously, gravimetric analysis is an analytical technique strictly based on the measurement of mass. You precisely measure the mass of an initial unknown substance, and then you precisely measure the mass of a resulting precipitate, of which you know the composition of the precipitate, you know the chemical formula of the precipitate, and then as a result of the analysis, you're able to determine the percent composition by mass of a specific element in the unknown substance. Okay, but now titrations are a little bit different. With a titration, you're measuring the volume of a solution needed to completely react with another solution. The unknown in a titration is the concentration of a solute in the unknown solution. So in a titration, there's the unknown solution, and then there's a second solution called the standard solution, of which the concentration is precisely known. And the idea is you're going to titrate the unknown solution against the standard solution to determine the concentration of a solute in the unknown solution. Okay, so a general way you can think about how this works is, so okay, let's think about, you have a beaker and a burette. The solution in the burette is added to the solution in the beaker, with the exact volume of burette solution added being tracked, because the burette is scaled. Okay, now at some point called the equivalence point, all of the dissolved molecules or components in the beaker solution that are involved in the titration, involved in the chemical reaction of the titration, are going to be completely reacted with, which means that the next drop of solution from the burette into the beaker solution past the equivalence point is going to cause a distinct change in the nature of the beaker solution that can clearly be identified via an indicator. Okay, and so with this indicator of the equivalence point, this is a signaling that the titration is complete and you want to stop adding, you don't want to add any more of the burette solution. Okay, and so now with the titration complete, because at the equivalence point, you know all of the components of the beaker solution were reacted with, and you know exactly how much volume of the burette solution was added to get to the equivalence point, to get to the precise point where the very last dissolved component of the beaker solution was reacted with, you can determine the concentration of the unknown solution. That's how titrations work, any kind of titration. Okay, now with acid-base titrations, as we talked about, the chemical reaction taking place in the titration, or the chemical reaction that takes place upon the mixing of the burette solution with the beaker solution, is an acid-base neutralization reaction. So an acid and base interact to form a salt and water. The neutralization is in the form of H plus ions reacting with OH minus ions to form water. And the change in the nature of the beaker solution at the equivalence point is the solution going from acidic to basic or vice versa. Okay, and now a redox titration is the exact same idea as what we learned with acid-base titrations, right? The term titration is a general term. Acid-base titrations and redox titrations are both just titrations. Okay, and so it says, as mentioned earlier, redox reactions involve the transfer of electrons, and acid-base reactions involve the transfer of protons. Just as an acid can be titrated against a base, we can titrate an oxidizing agent against a reducing agent using a similar procedure. We can, for example, carefully add a solution containing an oxidizing agent to a solution containing a reducing agent. The equivalence point is reached when the reducing agent is completely oxidized by the oxidizing agent. Like acid-base titrations, redox titrations normally require an indicator that clearly changes color. In the presence of large amounts of reducing agent, the color of the indicator is characteristic of its reduced form. The indicator assumes the color of its oxidized form when it is present in an oxidizing medium. At or near the equivalence point, a sharp change in the indicator's color will occur as it changes from one form to the other, so the equivalence point can be readily identified. Okay, so again, a redox titration is a titration just like an acid-base titration. Both are titrations. And as we just talked about, in a titration, in a general titration, what we're doing is we're mixing a solution of unknown concentration with a standard solution of known concentration to determine the concentration of a specific solute in the unknown solution. Okay, but like it said here, instead of titrating an acid against a base or vice versa, as is the case with acid-base titrations, with redox titrations, we're titrating an oxidizing agent against a reducing agent or vice versa. So as we talked about with acid-base titrations, an acid or a base could be the standard solution or the unknown solution. It doesn't matter. It's the same idea with redox titrations. You could have the oxidizing agent or reducing agent be associated with the standard or the unknown solution. It just depends on the titration. Okay, so if we take a look at this example here, let's come to this example right now. Here, they're talking about titrating an iron sulfate solution against a potassium permanganate solution, where in this case this would be a redox titration, because the titration it's not based on a neutralization reaction, an acid-base neutralization reaction. The titration is based on a redox reaction. Okay, and so the goal is, since, like I just said, they're titrating the iron sulfate solution against the potassium permanganate solution. Well, that means that the iron sulfate solution is the unknown solution. Okay, and so the goal is they're trying to determine the concentration of the iron. So the Fe, this is iron 2 sulfate, the Fe2 plus ions in the unknown solution, in the original unknown solution. Okay, and now here on the right, you can see that they have a burette beaker setup. In this case, they've got the standard solution, the potassium permanganate solution, in the burette, and the unknown solution in the beaker. Okay, but if you remember, for the main acid-base titration example that the textbook gave in the previous section with the KHP acid and sodium hydroxide, it was the opposite. The KHP was the standard solution that was in the beaker, and the sodium hydroxide unknown solution was in the burette. Okay, but it doesn't matter. You can do this whatever way works best. Okay, but now with the unknown solution, no matter which way you do the titration, adding the unknown to the standard or vice versa, you're going to need to record exactly how much volume of unknown solution that you either, if the unknown solution is in the beaker, how much you started with before starting the titration, or how much the unknown solution was added. So in this case, with the unknown solution in the beaker, they recorded exactly how much unknown solution was started with, 25 milliliters of the iron 2 sulfate. Okay, but now for the standard solution in this case, in the burette, you're going to be tracking exactly how much of this solution is added during the titration using the scale on the burette. But then at the same time, for any titration, when it comes to the standard solution, you're going to know the precise concentration of the standard solution, and that's what they give here. Standard solution concentration is 0.1327 molarity of potassium permanganate. Okay, so now we can think about how initially in the beaker solution, you're going to have Fe2 plus and SO42 minus ions, right? Here you've got iron 2 sulfate, an ionic compound. It's soluble, a strong electrolyte. And in the standard solution in the burette, you're going to have dissociated dissolved K plus and MnO4 minus ions, potassium and permanganate ions. Once again, this is just another soluble ionic compound. It's going to dissociate into ions. And also note that just like with the gravimetric analysis and acid-base titration problems we looked at in the previous sections in this chapter, we aren't thinking about solubility of components being a factor. We'll consider solubility equilibrium in relation to gravimetric analysis and titrations in chapter 16. Okay, so now when the solutions are mixed, when you start the titration, you start to add the burette solution, the standard solution here, to the unknown solution. A chemical reaction takes place. Specifically, with the redox titration here, this is going to be a redox reaction. Okay, and the net ionic equation for this redox reaction is shown here. Now, this looks really complicated, but don't worry about this type of reaction too much right now, because to understand where this net ionic equation is coming from, you have to consider that the iron 2 sulfate solution is also acidic as well. So, like, you dissolve the iron 2 sulfate into an acidic aqueous solution. Like it says here, this is in an acidic medium. Therefore, once the two solutions are mixed, what you technically have is a chemical reaction taking place in an acidic solution. Okay, and we're going to learn all about balancing redox reactions that occur in acidic and in basic environments in chapter 18. Okay, but trusting that this net ionic equation is correct and not worrying about where it comes from at the moment, first, let's remind ourselves of what exactly a net ionic equation is. Okay, with a net ionic equation, the idea is you might have all kinds of different ions floating around in this solution, right, when the burette solution is added. But the net ionic equation is just showing you strictly the ions in the solution that are involved in the chemical reaction. Okay, and so again, at the start of the titration, when you begin adding the standard potassium permanganate solution in the burette into the unknown iron 2 sulfate acidic environment solution, all of these dissolved ions interact and a chemical reaction takes place with the balanced net ionic equation for this chemical reaction shown here. Okay, so what are the redox characteristics of this reaction? Okay, well, we can see that iron gets oxidized. We go from +2 here to +3 here. Hydrogen doesn't change oxidation state. Neither does oxygen, because, okay, we know the oxidation states of hydrogen and oxygen in H2O. It's going to be +1 and -2. Okay, so now you can see that hydrogen doesn't change oxidation state, but now with the permanganate ion, the oxidation state of the 4 oxygens are going to be -2, right? Because there's no cardinal rule here that's going to force oxygen to deviate from its -2 oxidation state. And so that's how we can see that the oxygen doesn't change oxidation state in this chemical reaction. But now the sum rule is going to dictate the oxidation state on the manganese here in the permanganate ion. So you've got -8 plus X needs to equal -1. So the oxidation state on the manganese is going to be +7. Okay, but now the manganese on the product side here, manganese 2 plus cation has the oxidation state of +2. And there you go. So manganese is reduced. So in this reaction, iron is oxidized and manganese is reduced. Iron is the reducing agent and manganese is the oxidizing agent. Okay, and so the idea of the redox titration process that's being conducted here is this. Remember, with a redox titration, you're titrating an oxidizing agent against a reducing agent or vice versa. In this case, for this example, we're titrating a reducing agent against an oxidizing agent. The reducing agent is Fe2+, and the oxidizing agent is MnO4-. Okay, and so if we keep reading, it says 2 common oxidizing agents are potassium permanganate and potassium dichromate. As the above figure shows, the colors of the permanganate and dichromate anions are distinctly different from those of the reduced species. So what they're saying is that if you've got dissolved permanganate ions in solution, that's going to result in a purple color of the solution, as opposed to the corresponding reduced species of this permanganate, in which case, as we just saw, the manganese goes from a +7 oxidation state to a +2 oxidation state. If you had dissolved manganese 2 plus ions in solution, so you don't have, so they're referring to like, okay, these are no longer present. If you just had dissolved permanganate, you're going to have a purple solution. If you just had dissolved manganese 2 plus ions, you're going to have a light pink solution. Okay. Another case is if you only have dissolved dichromate ions, then you're going to have an orange yellowish solution. But then the corresponding reduced species where the chromate gets reduced, if you had just dissolved Cr3 plus ions, then the solution is going to be green. Right, so if we come here, then that's what they're showing. This is dissolved permanganate. This is dissolved Mn2 plus. It looks colorless, but that's what they refer to as light pink. Here's the orange yellow dichromate, and here's the green Cr3 plus. Okay, and so it says, thus these oxidizing agents can themselves be used as internal indicators in a redox titration because they have distinctly different colors in the oxidized and reduced forms. Okay, so note the difference with acid-base titrations in that, remember, a separate substance independent from the titration chemical reaction was needed to indicate a change in the acidic or basic environment. It was mentioned how a commonly used indicator for acid-base titrations is phenolphthalein, which is colorless in acidic and neutral solutions, but reddish pink in basic solutions. Okay, but like they're saying here with the redox titrations, you're not going to need to bring in a separate substance to use as an indicator. The components themselves involved in the redox titration, involved in the chemical reaction, act as the indicators, right? The oxidizing and reducing agents themselves. Okay, and so coming back to the example problem, initially, before the titration starts, the Fe2 plus ions in the unknown solution are going to produce a pale green color. And in the standard solution, the permanganate ions, the MnO4- ions, are going to produce a purple color, right? So like if you're confused looking at the net ionic equation, remember, this is what happens upon mixing. All I was just referring to was prior to the titration starting, prior to any mixing, you've got this acidic iron sulfate solution. So there's H+, there's Fe2+, and SO4 2- ions floating around everywhere. And the Fe2 plus ions are going to result in this, or are going to be the main contributor to this pale green color. And then before the titration starts, in the standard solution, you're going to have K plus and MnO4 minus ions, and the MnO4 minus ions are going to be the primary contributor to this purple color. Okay, now upon mixing, what you can think about is, so if you had a solution that had only Mn2 plus and Fe3 plus ions, hypothetically, if off to the side you had a solution that had only these two ions dissolved, with no other ions present that would contribute to a color, then the solution would be colorless. Okay, so keep that in mind. Mn2 plus and Fe3 plus ions in aqueous solution is colorless, or at least close to colorless, nearly colorless. Right, so like we talked about here, it said that dissolved permanganate is purple, but Mn2 plus is light pink. Well, if you look here, there's the purple they're referring to, and there's the light pink they're referring to. Okay? So, as the titration is being carried out, initially, when some standard solution is added to the unknown solution, like it shows here, you see purple in the solution. But this purple quickly disappears. Okay? But so why? Why does it disappear? Well, because the purple MnO4 minus reacts with the Fe2 plus and in combination with H plus ions to produce the products, the colorless or nearly colorless products. And so after some standard solution is initially added and chemically reacts and disappears, what you're left with in the beaker in terms of color is less Fe2 plus ions than what you started with, and more Mn2 plus and Fe3 plus ions than what you started with, right? So what that means is that the solution is getting paler and paler, getting closer and closer to colorless. And as you keep slowly adding more and more and more of the standard potassium permanganate solution, the solution in the beaker is getting more and more colorless, right? And then as you approach the equivalence point, once you get near the equivalence point, you're almost out of Fe2 plus, and what's predominating is these reactants here. So as you get near to the equivalence point, you're getting a nearly colorless solution in the beaker. Okay, but now at the equivalence point, what happens? What happens at the equivalence point? Well, at the equivalence point, the idea is you've added the last drop of the potassium permanganate solution to where the last remaining Fe2 plus ion gets reacted with the permanganate. And so now from there, if you add an additional drop of the standard solution past the equivalence point, you're going to have dissolved permanganate that's not going to have Fe2 plus to react with. And so what does that mean? Well, what that means is that the solution is going to dramatically change color towards purple, because you're all of a sudden going to have permanganate ions floating around because they're not reacting with anything and disappearing like they were before. And that's the indicator of the equivalence point, okay? And at the completion of the titration, you know exactly how much volume of the standard solution, the potassium permanganate solution, was added to the beaker, to the unknown solution, in order to completely react with all of the Fe2 plus ions that were initially present in the unknown solution. Okay, and so since you know the volume of the standard solution added to get to the equivalence point, and you precisely know the concentration of the standard solution, well, then you know how many moles of the oxidizing agent, the permanganate ion, reacted with the Fe2 plus ions that were initially present in the solution. Okay, but now then how many moles of Fe2 plus ions reacted with those moles of MnO4 minus ions? Well, this might not be a one-to-one relationship, right? So stoichiometry with the net ionic equation is used to figure out how many moles of the reducing agent, Fe2 plus, reacted with the oxidizing agent, MnO4 minus. Okay, and then now from there, knowing the number of moles of the Fe2 plus ions present in the initial unknown solution, and also because we made sure to record the initial volume of unknown solution, 25 milliliters. The concentration of Fe2 plus in the unknown solution can be determined. Okay, so that's how redox titrations work. Okay, and it says redox titrations require the same type of calculations based on the mole method as acid-base neutralizations. The difference is that the equations in the stoichiometry tend to be more complex for redox reactions. Yeah, so remember, you still have to do some stoichiometry with acid-base titrations. Stoichiometry like we had to do here at the last stage for this example problem. We had to go from the moles of permanganate ion to moles of Fe2 plus. Stoichiometry is necessary with acid-base titrations from the standpoint of, so like we talked about, what if you're performing the titration with a diprotic or triprotic acid? Or what if you're performing the titration with a base like barium hydroxide, BaOH2, which yields 2 OH minus ions for each barium hydroxide unit? Well, yeah, so you've got to do stoichiometry to figure out exactly how many moles of the unknown solution acid or base reacted with the corresponding number of moles of the standard solution acid or base, right? Okay, now, but it says with redox titrations, the equations and the stoichiometry tend to be more complex. Well, yeah, especially if you're having to analyze the entire redox reaction in solution from scratch, then as we talked about, like for this problem here, you have to know how to set up and balance the redox reaction taking place in acidic solution. Okay, but again, for right now in this chapter for redox titrations, don't worry about where the chemical equation corresponding to the redox titration, the net ionic equation, comes from. That's just going to be given to you. Don't worry about where that comes from right now. All you need to be able to do for a redox titration problem in this chapter is, so okay, you'll be given a balanced net ionic equation that corresponds to the redox titration. Go through the net ionic equation and assign all of the oxidation numbers. I identify what is being oxidized and what is being reduced. So identify what element and the corresponding compound it's in is the oxidizing agent, and what element and compound is the reducing agent. Okay, don't try and write out the half reactions. Those get complicated as well when you're dealing with redox reactions in acid or base environments, basic environments. So don't write out the half reactions. You won't know what you're doing. We'll learn about all of this in chapter 18. Okay, just write out the oxidation numbers and identify, okay, here's what's getting oxidized, here's what's getting reduced, here's the oxidizing agent, here's the reducing agent. Okay, and then just go ahead and identify which of the oxidizing and reducing agent, which is associated with the standard solution and which is associated with the unknown solution, just so you can understand the whole titration. Okay, and then there's going to be 4 total components involved with the redox process. You're going to have the oxidizing and reducing agent compounds on the reactant side, and then what these compounds are transformed into on the product side. Okay, and then from there, do a Google search to find out the colors in aqueous solution of these 4 different species. These colors are going to give you a visual for the starting colors of the standard and unknown solution. Okay, you'll also have a visual for how the burette solution color immediately transforms once added to the beaker solution as a result of the chemical reaction, and then how the beaker solution color slowly changes as burette solution is added. Then you'll also get a visual for what the color of the beaker solution is as the equivalence point is approached, and you'll have an understanding for what the indicator is going to be once a single drop of burette solution is added to the beaker past the equivalence point. Okay, and then from there, just take the information that's given to you regarding the concentration and volume of the standard solution and the volume of the unknown solution, and use that information with the balanced net ionic equation that's given to you to determine the concentration of the unknown solution.